IPA members, students, we welcome you all for today's DAE CV Raman lecture talk by Dr. Sita on studies of compact objects using AstroSat in collaboration with IPA and BRNS. We request Professor Dr. Vandana Nanal, IPA Secretary, to enlighten us with the IPA activities. Over to you, ma'am.
Thank you, Dr. Sarla. Give me a minute to share my screen. I think you all can see my screen now. Yeah. So good afternoon and a very warm welcome to all the viewers and today's speaker, Dr. Sita. I am also very thankful to Vivekananda Education Society College for hosting this IPA DAE CV Raman lecture. Let me just take a couple of minutes to tell you about Indian Physics Association. Many of you would have heard about it, but IPA or Indian Physics Association was founded in 1970, almost 5 decades back, with a goal to provide a platform for interaction of physicists, physics students, people interested in physics research, so that they can be acquainted about keeping their general interest in mind about the developments in the field. This is achieved by publication of bulletins. IPA brings out a quarterly bulletin called Physics News, and this is now published online and several back issues are also available online. The IPA brings out time to time reports and some special books. But a majority of effort goes in arranging various seminars and special programs, lectures, especially for students and young researchers, acquainting them of the latest developments. So some of the lectures IPA organizes are DAE CV Raman lecture series, which today's lecture is a part of it. IPA also liaises with other international bodies like Institute of Physics UK and APS, also the AAPPA, that is Association of Asia Pacific Physical Societies. So some lecture series are also held together with them. One of the prestigious series is the IPA IOP Bhabha Cockcroft-Walton Exchange Lectures. These lectures are alternately held between in India and in UK, and in India they are called Cockcroft-Walton lectures, and in UK they are called Bhabha lectures. In addition, there is a Professor P.A. Pandya Endowment lecture which is held annually. With the pandemic, several of the IPA programs were curtailed, were forced to be online, and we had a webinar series, New Horizons in Physics, to commemorate 50 years of IPA. Since then, we also have an IPA monthly colloquia series. It happens on the first Saturday of the month, or if the first Saturday happens to be major holiday, then on second Saturday of month. And all these events are available on IPA YouTube channel. And the information about it, more information can be found at our webpage, and I will put this address in the chat box also. IPA gives several awards biennially for the senior scientists and the young physicists to both as to acknowledge their accomplishments to the field and contributions to the field. The current office bearers of the IPA are Professor S. Ramakrishnan, Director TIFR, is the President of IPA. Professor Tanushree Saha Dasgupta, Director SN Bose Center, Kolkata, is the Vice President of IPA. Myself, Vandana Nanal, General Secretary. Professor Samit Mandal from Delhi University, Joint Secretary. Dr. Aradhana Srivastava from BRC is Treasurer. And IPA 2 years back also established a gender in physics working group. This is particularly aimed at addressing the gender paucity in physics profession in Indian context. And Professor Shubhapati Goswami is the current chair of this group. The DAE CV Raman lecture series is supported by BRNS, and we hold 5 lectures every year at different places and covering different areas. And these lectures are delivered by eminent scientists and aimed at the undergraduate and graduate students aspiring to pursue a career in physics. And today's lecture will be given by Dr. Sita. We are particularly happy to have her at today, because as we all know that February 11 is the International Day of Women and Girls in Science, and March 8 is International Day of Women. So we are very, very happy to showcase the work done in India by women scientists and bring this thing to you. Once again, thank you all for joining us today for this lecture, and I'm sure you will find it very, very interesting. So over to you, Dr. Sarla.
Yes, thank you, Professor Dr. Vandana Nani. Now we request our principal, Dr. Anita Kanwar, to talk about our physics department and college. Over to you, ma'am. Can you hear us, Anita ma'am? Ma'am, can you unmute?
1 minute, I have to give her I have to unmute. She should be.
Thank you, Sarla. I hope I am audible now.
Yes.
Yes, please.
Okay. So good afternoon and warm welcome to today's esteemed guest, Dr. Sita, an outstanding scientist from ISRO, and presently she's an emeritus scientist at Raman Research Institute, Bangalore. Professor Vandana Nanal, Indian Physics Association Secretary. Dr. Aradhana Srivastava, Treasurer IPA and Senior Scientist at NPD, DARC. Board of Research in Nuclear Sciences dignitaries, our Vice Principal, Dr. Shantini Nair, members of Physics Department, all invitees, and my dear students. Thank you all for joining this informative session on behalf of Vivekanand Education Society's College of Arts, Science and Commerce, Chembur, Mumbai. Madam, I will first briefly introduce you to our college. Our college is affiliated to Mumbai University, and we are NAC accredited with A grade college situated in Chembur, Mumbai. The main emphasis of our college is on value education and character building. We run 29 courses under aided and self-financing sections, which include 17 undergraduate programs, 9 postgraduate programs, and 3 PhD courses. We have received Best College Award from University of Mumbai under Urban Area category. And we are also recipient of many grants, out of which the few noteworthy ones are Feast Grant from DST, Government of India, and Star College Grant from DBT, Government of India. Recently, we are awarded with autonomous status by UGC, and which is confirmed by University of Mumbai. And all these became possible due to very supporting management and ever encouraging and dedicated staff members, and also our hardworking students. Department of Physics with all its members have contributed immensely in the progress of institution and for motivating students to take up career in physics, especially in physics research. Our students have cleared many competitive exams and bagged position in national and international institutes of repute. We are privileged that Dr. Sita, who has significantly contributed in the Mars mission also, is going to address our students. Madam, we are really thankful to you and BRMS for funding this seminar. Thank you all for joining this webinar. Over to you, Sarla.
Thank you, madam. Now I request our in-charge HOD, Devidas sir, Dr. Devidas Gulwade, to introduce today's speaker, Dr. S. Sita. Yes, 1 minute. I'm doing. Sir.
Yeah, thank you, ma'am. It is a great privilege to introduce Dr. Sita. Dr. Sita is PhD in physics from IISc Bangalore. Dr. Sita superannuated as outstanding scientist from the UR Rao Satellite Center in January 2019. After serving in ISRO for nearly 39 years, she has coordinated as director at the Space Science Program Office at ISRO headquarters and contributed in various space science activities at ISRO. At present, Dr. Sita is Emeritus Scientist at Raman Research Institute, Bangalore. She is also the principal investigator of the AstroSat, the first dedicated space astronomy mission since April 2011. She has contributed extensively to the development of the space science instrumentation for Indian science payloads. She has contributed significantly to the Mars Orbiter mission also, which is famous as Mission Mangal. She is eminent scientist and received various prestigious awards such as CV Raman Young Scientist Award in Physical Science in 2003 and Best Woman Scientist Award in 2012, to name a few. She has over 80 publications in various referred journals and has guided 5 students for PhD. We all are eagerly waiting for the talk of Dr. Sita. We request Dr. Sita to start the talk. Over to you, ma'am.
Thanks to you, Professor Vandana, Professor Sarla Rati, Dr. Anita. Thanks for the kind introductions. And also I thank Indian Physics Association for giving me this opportunity to address you all. And I hope we will have a good session today. I also thank Vivekananda Education Society for hosting this event. In today's talk, what I will try to do is briefly tell you the portions where physics is applied to various aspects of our understanding in stars and stellar systems, with specific emphasis on observations made by the AstroSat. Yeah, so the first half of this talk will be a sort of introduction, which will be followed by results. Yeah, so many of you have seen stars in the dark sky. And if you have access to a really dark location, you would have seen a splendor of stars, like is shown in this picture, which is taken from the Himalayan Chandra telescope location, which is very, very dark, and you can see the spiral arm of the galaxy indicating billions of stars. So today we will address the question that the stars which appear to be lasting forever and ever, are they really permanent as they are, or do they change over long periods of time? Next slide. Okay, so it's gone to the third slide. Can you go back to the previous slide, please? The sun, as we see it, for example, is an yellow star, right? And we know that the temperature of the surface of the sun is 5,800 degree Kelvin. Now, what is Kelvin? Because there might be students from outside the physics community, I will slightly explain even basic things like Kelvin. Kelvin is another scale for temperature, just like the centigrade and Fahrenheit, which you are very familiar with. Kelvin, 0 degree Kelvin corresponds to minus 273 degrees centigrade, and it is considered the absolute zero in the universe. So all of our astronomical observations are made in terms of Kelvin. Yeah. The emission from the surface of the sun can be approximated to a black body. Not only the sun, but also the other stars, which emit in the visible spectrum, can be approximated to a black body. The physics students would have learned about Planck's law and black body spectrum. So the black body spectrum peaks at a particular wavelength, and there is a wavelength to temperature correspondence as approximated by Wien's law of the black body spectrum, and that gives us the temperature of the surface of the star. So as I said, the peak wavelength of sun's emission falls around 550 nanometers or 5,500 angstroms, which corresponds to the yellow light which we see from the sun. So there are many stars in the sky, as you would have seen, which are slightly bluish in the color, like the Sirius. And there are also stars which are redder, like the Betelgeuse. So the Sirius, the blue stars are hotter than the sun, and the red stars are usually cooler than the sun. So then the how do we know this? By the Wien's displacement law. So if it is hotter, the peak emission shifts to the bluer side, and if it is cooler, it shifts to the redder side. And that's how we can estimate the surface temperature of various stars. And in fact, if they are much hotter, like for example, tens of thousands of degree Kelvin, then they can also peak at UV wavelengths. Yeah, okay, so next slide. Most of the stars which we observe is through this radiation which they emit, which is termed as the electromagnetic radiation. So the star itself, like the sun, as I said, can be approximated as a black body. Of course, there are other ways, other emissions which may not be black body, which also emit electromagnetic radiation, as we will learn in the rest of my talk. So if you see the electromagnetic radiation, the visible part is what we see daily, through which we see with our eyes, which is accustomed to this visible part of the spectrum. So if you go to the red part of the visible part and go further in wavelengths which are longer, we come to the infrared, and further down we can go to the microwave, and further longer waves are what is called the radio wave part of the spectrum. Now the infrared, as you know, is used in remotes of our TV. It is also used, the microwave is used in microwave ovens, and radio part, of course, is used in the radio part of the spectrum, which is used in radio transmission and radio waves, which we get from the celestial sources. On the left-hand side, you see, left-hand side of the figure, if you go bluer than the visible part of the spectrum, you will see ultraviolet, and beyond that, you can see the X-rays, and further down, shorter wavelengths will be the gamma rays. Yeah, on the right-hand side of the figure, on the slide, which you see, it shows the atmospheric transmission to these important wavelengths of the electromagnetic wave spectrum. So if, for example, a star emits in each of these wavelengths, can we observe them from the ground is the question. So as I told you, the visible part of the spectrum reaches all the way to the surface of the ground. So also the radio part of the spectrum from celestial sources reaches all the way to the surface of the ground. And that's why we have a lot of optical observatories and radio observatories constructed on the ground. Some of the optical observatories also extend to slightly in the infrared region at higher heights. But in the longer wavelengths of the infrared and also in high energy gamma rays, we can observe from balloon heights of 30 to 40 kilometers. And there is a balloon facility operated by the Tata Institute of Fundamental Research, Mumbai. And this facility exists at Hyderabad, and they can have balloons up to 40 kilometers, depending on the mass of the experiment. What do we do about wavelengths which are shorter than the blue, that is the UV and the X-rays? As you can see, this is again absorbed, as can be shown by the violet cross-hatched regions on the right-hand side drawing. And so it cannot be observed on the surface of the earth. We need to go to heights beyond about 150 kilometers or one minimum of 120 kilometers. We need either rocket to observe in the ultraviolet and the X-ray domain. Yeah, next slide. So do we, for example, know that the stars, how do they shine? How and do they shine forever? So let us take the sun, for example. The sun shines, as you would have all heard, due to the nuclear fusion energy which happens at the center of the, or at the core of the sun. Now, the nuclear energy, as I said, is corresponding to hydrogen fusion, and hydrogen gets converted to helium in the core of the sun. Yeah, and so this happens at the core of many stars like the sun. And this nuclear reaction is very critically dependent on the central density and the central temperature which a star achieves at the core of the sun. So that can lead to the conversion of hydrogen to helium. And in slightly more massive stars than the sun, the helium can further go into nuclear reaction and can get converted to carbon or oxygen also. But how does the sun balance itself? So the balancing is done based on the self-gravity of the mass of the sun, and which is balanced by the outward pressure caused due to the gas pressure and the radiation pressure, which is existing at every radius of the sun, considering the mass which is contained within that radius. Now, how do we know that this is indeed happening, that the nuclear reactions are happening at the core of the sun, etc.? These nuclear reactions actually lead to the creation of neutrinos, and neutrinos, as you know, hardly interact, and so they can escape from the core outside the sun and can reach the earth, and even can go, some of them can go through the surface of the earth also. So we have several observatories to observe these neutrinos, and recently we have also discovered that indeed the number of neutrinos we observe can be explained, can be used to explain that the nuclear reactions are indeed happening at the center of these stars. Next slide. Okay, so so I asked the question, do they shine forever? Of course, they shine for millions of years. And so as far as humans are concerned, it is well beyond our life cycle of of 100 years or so. But if I ask the question, do they shine forever like this with nuclear fusion happening at the cores, then what happens to the sun when it exhausts the hydrogen fuel at the center of the sun, and everything, the whole core is converted into helium. Now, as I said, again the gravity will take over and the core will contract. If the helium can achieve densities and temperatures which can then get converted to carbon and helium, then that nuclear reaction will again take over, and again the hydrostatic equilibrium will be maintained. However, if the central core density and the temperature when the helium contracts cannot achieve that temperature, then the core will end up as a helium core. Now, what happens to the helium core? It continues to contract and contract and contract till the core becomes degenerate. In that case, the electron degeneracy pressure will balance this contraction, self-gravitation, and therefore, at that stage, the central degenerate core will end up as what is called a white dwarf, which will consist of, in the case of the sun, most probably as a helium core. At that stage, the sun would have contracted to the radius of the earth. As you know, the radius of the sun is 100 times the radius of the earth, but when it becomes a white dwarf, the white dwarf will have approximately half times the solar mass which it has right now, because the outer layers will expand and will be thrown off, but the central core will still have approximately half the mass of the sun. But the radius, as I said, will be the radius of approximately the earth. So it will appear as a blue, small, degenerate core with a temperature of around 100 degrees Kelvin. So this will be very hot, and that is why it is called white, and it will be very small, and that is why it is called a dwarf. And the outer layers will expand and will be thrown off as what is called a planetary nebula. How do we know this? We can observe such planetary nebulae in our galaxy and some of them outside our galaxy. The lower bottom picture shows the Hubble Space Telescope picture of a planetary nebula called the Spirograph Nebula, at the center of which there is a white dwarf. And this nebula contains all the matter which is thrown off when this star went into a red giant phase and the core formed a white dwarf. Next slide. Because the important thing I have to tell you about white dwarf is that the gravity, because it has the mass of nearly the sun, but the radius of at the radius of the earth, the gravity of this white dwarf is about 10,000 times more than the gravity on the earth, which is around 1,000 centimeter per second squared, right? 980 centimeter per second squared, which I can approximate it to be 1000. Yeah. Whereas the gravity on the surface of the white dwarf will be 10 to the power 7 to 10 to the power 8. So 1 kg mass on a white dwarf will weigh 10,000 kgs on the surface of the white dwarf. So the next question, so white dwarf is one of the compact objects which I will be talking about. What happens to more massive stars, like say 10 times the solar mass? Do they also end up as white dwarfs? No. White dwarf 1.4 solar masses as expressed by the Nobel laureate Professor Chandrasekhar, which is termed as the Chandrasekhar limit. So when there is a massive star, what happens, as I said, is that indeed as the core contracts, the temperatures and densities can be achieved where the helium gets converted to carbon, oxygen, and then that core contracts and it can go on to neon, magnesium, etc., etc. And then finally it goes to silicon, and final element is the iron core. Now, the binding energy per nucleon for iron is the maximum, and beyond that, it decreases with increasing mass of the element. And therefore, beyond iron, you can't form in this kind of reaction. And so what happens is, the core at that stage is not even degenerate, and so it contracts and contracts. Then what happens is, you achieve what is called nuclear densities, and at that stage, there can be inverse beta reactions, and so electrons can penetrate into the nucleus, and protons and electrons can combine to form neutrons. And so what is left behind when such a star implodes to form a degenerate core is a core consisting of only neutrons, and the outer layers are blown off in what is called a supernova explosion, and the core consists of neutrons, and it is a huge neutron star. So what holds up this core is again against gravity of its central mass, is again the degeneracy pressure of the neutrons, because again neutrons are leptons and they follow the Fermi-Dirac statistics and therefore follow the Pauli exclusion principle. And so you can't combine, you can't place neutrons much closer than what is allowed by the Pauli exclusion principle, and therefore the degeneracy pressure of neutrons will balance the self-gravitation of the core. Yeah, at this stage, the gravity of the central neutron star is now 10 to the power 14 to 10 to the power 15 grams per second, centimeter per second square, and therefore it is of the order of 100 billion times the gravity of the Earth. So this is what you have to remember when I talk about observations. Next slide. So can all stars end up as neutron stars? No, if the core exceeds, for example, core which is left behind exceeds 3 solar masses. Ideally, it is 6 solar masses, but we find experiment observationally that we don't find neutron stars beyond 3 solar masses. So most likely anything beyond 4 to 5 solar masses cannot even end up as neutron stars. They go into what is called the black hole. So there what happens is there is no pressure gradient which can balance the self-gravity, and the gravity of these stars is the ultimate, and it compresses all this 4 to 5 solar mass in the core to a point mass, or this is what is called a singularity, because it goes to point, which means the radius of such an entity is essentially 0. But it can have any mass from, say, few stellar masses to few billions of stellar masses, which is called the supermassive black hole. So how do we observe these black holes is what I will tell you in the rest of my talk today. And the first actual image, how do we know about the black hole? Because you have heard that whatever enters close to the black hole can never be seen. Even light cannot escape from the black hole. So what we see is actually what is outside what is called the event horizon of a black hole, which depends on the mass of the black hole. And such an event horizon has indeed been observed in radio waves using the Event Horizon Telescope, which consists of a series of telescopes, and they achieve resolution of 25 micro arc seconds, which is much better than the resolution achieved by Hubble Space Telescope. And you see that matter goes around this supermassive black hole, and indeed we see something like a disk around this black hole. Next slide. So how do we observe these neutron stars and black holes? Many of these compact objects like neutron stars and black holes are in binaries. They can then attract, because of their strong gravity, they can attract mass from the companion star during the binary evolution. So what happens is the outer layers of the companion star go through the central Lagrangian point of this binary system, and they get attracted to the strong gravity of the compact star. And they form a disk around the compact object, and they gradually, due to viscous friction, they fall inside gradually and fall onto the surface of a white dwarf or a neutron star, if that is indeed the central compact object, or they fall beyond the innermost stable circular orbit of the black hole, which is beyond the event horizon, and then they of course fall into the event horizon. We can observe the emission coming from outside the event horizon and up to the innermost stable orbit. So do we see these objects around black holes only as disks, or even around neutron stars or white dwarfs for that matter? In addition to the disk, we know we have observational evidence that there is something called the corona. Now I have depicted this corona as a ring of matter around the compact object, but it need not have the shape. We in fact don't know the shape of the corona. It could be matter above the disk itself. It could be matter at a single point called a lamppost above the central black hole, maybe well above the event horizon. We don't know. But one thing we know is that the accretion disk is an optically thick and geometrically thin disk. And it also emits like a black body. Just like I said, black body emission, the sun's photosphere can be expressed like in the form of Planck's law or black body. The accretion disk is also emitting like a black body. However, the corona may not emit as a black body. It emits in a form of a power law. It can be a thermalized power law. It can be a Comptonized radiation. It can be anything. So we only know that it emits other than a black body. So when I continue my talk, you will know how we observe this. Now, in addition to this, some of the neutron stars, especially the young neutron stars, have very, very strong magnetic fields. In fact, even the white dwarf has a strong magnetic field, but the neutron star can have a magnetic field of the order of 10 to the power 12 Gauss. Remember that the Earth has a magnetic field of about 0.5 Gauss, and it can actually direct the charged particles coming from outside the atmosphere along the poles of the magnetic field of the Earth, and that is how the northern latitudes observe what is called the aurorae. In a neutron star, as I said, the magnetic fields can be as high as 10 to the power 12 Gauss, and so the accretion disk cannot fall onto the surface of some of these neutron stars which have these kind of magnetic fields, and the disk actually gets disrupted and it can flow along the magnetic lines of force and it falls on the magnetic poles of the neutron star. So when this happens, we can probably observe the neutron star. By the emission, it emits along the poles of this neutron star, just like a lighthouse emission. So we see emission like a lighthouse, and these are called accretion powered pulsars. Next slide. So now I will come to how do we observe this? There is one point I have to say. I talked about the accretion disk. I talked about the companion star. I talked about the central compact star. But remember one thing, and that is all these pictures, lovely pictures I showed you, are artistic depictions of these systems. When we observe these systems, we observe them as point objects like stars only. All this comes from the interpretation of the data we receive from these systems. So now I will talk about how do we receive data from these systems with particular emphasis to ASTROSAT. ASTROSAT is the first space astronomy dedicated mission of ISRO and therefore India. And we and this satellite observes in UV and X-ray bands. It is orbiting in a low Earth orbit of 650 kilometers and in a near equatorial inclination of 6 degrees. It has 5 experiments on board, one for both near UV and far UV, which is called the UV imaging telescope. The other 4 for covering the X-ray bands from 0.3 keV to 80 keV. Now, for those who are not familiar with keV, this is a homework for you. Wavelength of a blue light is approximately 2 to 3 electron volt. So I tell you, take this homework, convert wavelength to energy in ergs, and then convert ergs to electron volts, and see what these energies are. Yeah. So we have the soft X-ray telescope. We have the large area X-ray proportional counter, 3 numbers, and we have the cadmium zinc telluride imager covering this wide energy band from 0.3 to about 100 keV with a lot of overlap in the energy coverage, which is very important to actually intercalibrate each of these instruments, even though it is on the same satellite. And we also have a transient monitor called the Scanning Sky Monitor. This satellite called AstroSat is being operated like a space observatory, and we receive proposals from any scientific researcher in the world, and this is reviewed by a committee and accepted for observations, and then the satellite is turned in that direction to observe that particular source. Next slide. Now I will deal with what type of data is collected by these experiments. The first data is, of course, the imaging data. On the left-hand side, you see an image of a large circle, which corresponds to the full field of view of about half a degree of the UV imaging telescope, which has many stars, and somewhere close to the center, a little to the top, you see a galaxy, and that galaxy, when I blow it up, is what you see at the bottom of the left-hand side picture. This is NGC 2336, and this is a spiral galaxy. The image is taken using the UV imaging telescope. So the image tells us about what is the shape of the galaxy, where are the star-forming regions, etc., etc. We can identify many of these bright portions in this spiral arms and actually find out how many star-forming regions are there in this galaxy. About over 70 regions have been identified in this particular galaxy. Then we have what is called, on the right-hand side, temporal data, which is we can study the intensity of the source to which these instruments are pointed with time. Now, a source like the sun, if you observe, it might be constant normally, but it does emit flares, right? And you know that you see there are coronal mass ejections accompanied with flares. Now, if there is a flare on a sun, what happens is the intensity in some wavelengths will increase. So also I show a color graph in the center. This is corresponding to a light curve of a gamma ray burst. So normally the emission is low at background level, and suddenly there is an emission increase in the intensity with time, and then it decays. And this emission in the case of gamma ray burst, lasts only for few tens of seconds or maximum for few minutes. But this is what is called a transient. These transients can, as I said, in the case of gamma ray burst, can last only few seconds. In the case of black hole transients, can last several months. It can increase in intensity and last several months. On the right-hand side picture, I show a light curve which is periodic. This is due to observation of a neutron star. As I said, there is a lighthouse effect if we see the accretion powered pulsars, and therefore we see the spin of the neutron star in the form of variation in counts as the lighthouse spins around our line of sight. So we can determine the rotation period of the neutron star, and we can also see whether it is the same in different energies and so on. And then we come to the center bottom figure, and that is a typical variability from a black hole binary called GRS 1915. It is a highly variable source. You can see on the top two curves that it seems very periodic. It is of the order of 60 minutes. It seems to emit, but remember, it is long rise and short fall. And but this, after a few days, this changes. The variability changes both in shape and in period. And you can see this happens over a week or so, 10 days or so. So the variabilities change. So we need to study what these variabilities are caused due to and why this happens. So this is the temporal data. Next slide. In addition, in the temporal data, we had the x-axis as the time and the y-axis as intensity. In addition, we can have what is called the spectral data, where the y-axis is the intensity, but now the x-axis is energy or wavelength. Why do I say energy? Because X-ray photons are detected. Every photon is detected, and we can actually determine the energy of every photon. And we can construct this spectrum based on what energy each photon carries and create this spectrum. So this is a typical spectrum of a supernova remnant, and it shows emission lines corresponding to magnesium, silicon, etc. As I said, during the supernova explosion, the outer layers are thrown off, and indeed we see this in the X-ray spectrum of a typical supernova remnant. Yeah, this spectrum is taken from the soft X-ray telescope of AstroSat of the Tycho supernova remnant. I showed earlier the image of this in Chandra telescope. Now, with this background, let us look at some of the results. Next slide. So let us again start with white dwarfs. I showed you a planetary nebula and a central star. We observed a similar planetary nebula called the NGC 40, and this planetary nebula has been known for years now, and this is shown in the top figure, which is in the black background. The pink region, which is seen in this picture, is the planetary nebula. It is called the bow tie nebula because it shows an image like a bow tie. And it has a central white dwarf star. But that is the planetary nebula. But when we see it in the UV, we see a big halo of UV emission surrounding this planetary nebula, going well beyond the planetary nebula, which I hope you can see as a golden tinged halo within the black region. Can you see it? I hope you can all see it. It is a golden colored halo around the pink region. So what is this? It is a UV emission, far UV emission we see around this halo, around this nebula, and it is caused due to the fluorescence of most likely hydrogen molecules surrounding this planetary nebula. And so we think that much of the molecular hydrogen which was there before this planetary nebula emerged during the formation of the white dwarf still exists, and now it is being energized by the central white dwarf's emission from the central white dwarf, and it is fluorescing in far UV. The next slide, next result I show on white dwarf is that of a white dwarf binary called V3890. It is a white dwarf binary, and it actually accretes matter from a red giant companion star. Now, when this matter accretes, since white dwarfs has a surface, this matter keeps piling up on the surface of the white dwarf. Now, you may ask the question, you talked about nuclear reactions at the core of the sun. Can nuclear reactions happen elsewhere? Indeed, we find that when this matter from the companion star keeps getting accumulated, if the density of the accumulated layer and the temperature achieves the critical temperature needed for thermonuclear reactions, indeed, again, there will be a thermonuclear reaction, and it will blow away the accreted matter in the form of ejecta. This is shown in the bottom picture as an artistic depiction again. This is only artistic depiction. The white portion is the white dwarf, and the ejected matter is the white ring you see around it. And the red star is shown as the companion star. Now, how do we see this? It's only an artistic depiction based on what we have interpreted, right? So we observed this using the soft X-ray telescope, and we found that the ejecta is actually can be again modeled as a thermal spectrum, but this is of a low intensity. This right-hand side picture now is a little complicated to understand. I'll just try to explain to you briefly. The x-axis is energy. The y-axis is days after outburst. The top being 8th day and the bottom being 10th day. Now, the color coding is like this. Yellow is lower intensity, orange is next, red is next, and blue is highest intensity. So as you can see, there is a lot of soft X-rays, that is low energy X-rays. Like the middle energy X-rays remain orange and red throughout from 8th day to 10th day. However, the low energy X-rays are changing in color from yellow to blue. That means you see much more soft X-rays after 8.6 days or so. And this we interpret that indeed the outer layers are getting cleared and we see what is called a very, very soft source on the surface of the black hole. This is called the super soft source on the surface of the black hole, indicating that indeed the thermonuclear flash has occurred. Yeah, and this continues to be soft till about 19 days. And after 20 days or so, it again becomes yellow. This source has also been observed using the optical observatories on ground, including the Himalayan Chandra telescope. And we have results from this also saying that indeed in the beginning of the outburst itself, before these 8 days, etc., the ejecta indeed had velocities of about 9,000 kilometers per second. Yeah, so it's a big expulsion. Okay, so next slide.
Dr. Sita, may I request you to wrap up in next 5 to 10 minutes?
Hello, how much time do I have?
About 5 minutes. If you want 10,
okay.
it's
I'll
okay.
try to
Maybe
conclude
10 minutes.
quickly.
Yeah. 10 minutes.
Next slide. So similar thermonuclear bursts are indeed seen on neutron stars also. And that is the top left figure you see on 1636, a rare triple burst. This thermonuclear flash occurs within few minutes. Usually on neutron stars, we see such flashes occurring within few hours because, of course, as I said, the gravity on a neutron star is much more. However, this is a rare triplet which occurs within 3 minutes. So does it mean that the first one is only a partial thermonuclear burning and still some matter is left over? We don't know. And on the right hand side, you see a spin profile. I told you that we can see the spin profile of neutron stars. This is a spin profile of neutron stars. And because AstroSat can see energies up to 100 keV, we can, on the bottom right hand side curve, you can see that the spin profile can be seen as a function of energy. So the top second panel from the top is for low energies, and as you go down in the panels, it's higher and higher energies. So you can see the profile changes from double peaked to single peaked as we go higher in energies, and we can see it only up to 60 keV or so, and beyond that we don't see the spin profile. So we can model the emission around the poles of these neutron stars based on this spin profile. And on the lower left hand side, you see what is called a cyclotron feature, which is on the top. You see the complete spectrum, and you can't see anything much. You can see just a slight dip in the spectrum. When the continuum spectrum is removed, you see an absorption feature in the second panel. And that is a cyclotron feature at 18.5 keV, from which we can estimate the magnetic field of this neutron star to be 10 to the power 12 Gauss or higher. So similar results are obtained for several neutron sources. Next slide. And then I come to a similar cyclotron feature is observed also for another source called Hercules X1. And in fact, we can find that the cyclotron energy actually changes with time. So most likely, we can also study the magnetic field, how it is masked due to the incoming material on these kinds of stars. And then the disk can also be modeled from the FUV emission of this source. Yeah, next slide. And then I will end with result from a black hole binary. I told you many black holes actually are transients. They remain at background level. The accretion disk doesn't come close to the black hole, but then suddenly something triggers them to come to the black hole and we see an outburst. You just see the top panel, it increases in intensity and then gradually decreases in intensity over several tens of days. And from modeling of the spectrum of this black hole, we have taken data only in the blue bar shown in that figure. But with that small thing, we can find out the mass of the black hole by modeling the spectrum. And we also find oscillations called quasi-periodic oscillations at 2.2 Hertz. And these oscillations are strongly correlated to the coronal emission. And therefore, we think these oscillations have a coronal origin. Next slide. I think I will stop here. I will only say this, that we have also observed active galactic nuclei. And so we have observed emission around supermassive black holes also, as shown on the left-hand side. And we've also observed Lyman continuum, redshifted Lyman continuum emission from a galaxy at redshift of 1.42, where other observatories could not observe. Next. I will end leaving you with this last slide. There are many more results, and we have observed so far 1,400 sources of different types, and we have 1,500 users of registered users of this data who actually can download, either propose for observations or just download the data which is available and analyze this data. Astrosat has now completed almost 6.5 years in orbit. It was designed for 5 years. We have gone well past that, and we hope to get many more results from Astrosat. Thank you. Now open for questions.
Yes, thank you, ma'am. If you have
Thank you, Sarla, for sharing the slides. Sarla and team, I suppose.
Yeah, Vandana ma'am has a slide shared.
Yeah, thanks so much. Because I couldn't do it in the last minute. Yeah.
No problem at all. I think people can raise their hand and ask the questions.
Yeah, sure.
So then they can unmute one by one. So if there are questions, they can raise their hand. We will take first questions from Zoom. So I guess they'll take some time to type in. So Dr. Sita, just let me ask you one question, which is not quite the Astrosat related, but as we said, this is related to the occasion of also the Women's Day and this one. So would you give some guidance to the young people, young researchers who would want to do research in astronomy?
Yeah, okay. We have several young women scientists who have joined us and who are doing a lot of astronomy research, both from ground and from space. And astronomy is an area where you can get in, absolutely no issue. Earlier, we used to observe at the telescope floors. Now, in fact, data can stream into your rooms because the data can be collected and then can be sent to you, or in fact, you can get the data from other observatories all over the world using archival data also. So no issue at all. And as I hope I was able to convince you that a lot of physics can be applied in astronomy. In fact, astronomical sources are, I wouldn't say ideal, but they are exemplary laboratories for application of physics concepts. In fact, they are sites where you can apply strange physics also, which can be applied to normal laboratory physics also. So please do come in, all the girls, and there is absolutely no issue getting into astronomy. In fact, some of you, if you are adventurous, you can go to the sites which are often in dark, quiet, high altitude places, but very having very scenic beauty. So you can go to Hanley, for example. Within India, you can go to Kavalur, you can go to Mount Abu for optical telescopes, you can go to Devasthal, near Nainital. So very nice place. The observatories are located in very nice places. Of course, you also have radio telescopes in UT and also the GMRT in Pune. And there are many more facilities coming up. For example, to observe the gravitational waves, the LIGO India has been proposed. So, and the SKA for the radio telescope. So all these are also facilities which are coming up, and large telescopes like the 30-meter telescopes are also being proposed. So there's a lot of upcoming facilities also, and we also have the Aditya telescope coming in the space area, which will observe the sun. So it's not as if these are. So what I would advise to both women and men, do enter into this area of astronomy, and for the future missions, become mentors, because many of the younger girls would like to actually have advice from their seniors. And so we want to grow this community so that they will have women at all levels, not only at the student level, and don't drop off at the career level. Do stay on and continue your research right up to the top level, which you can achieve. And one more thing I wanted to say is, there are also initiatives from within India for citizen science also. So you can also even tell some of the women known to you who have already studied science but who are no longer in careers in science, can actually do science from home using citizen science thing. There is an initiative called RAD at Home, using radio astronomy data. So those who would like to do science but who want to stay at home can also contribute to astronomy.
Thank you so much, Dr. Sita, for giving a very nice overview and a very valuable advice. I see a hand raised by Dr. Devidas Gulade. So before I invite a question for him, I just want to add that the AstroSat was really something which we should really congratulate you all for, because this was India's first satellite laboratory, and it's been really working very fantastically. So congratulations to you. Sarla,
so
over
much
to you for handling the question.
Thank you so much. Thank you so much, Vandana. Yeah, Devidas, you can
Devidas, sir, can you? Yeah, Dr. Devidas Gulwade, can you ask?
Ma'am, I have a question, ma'am. How do we get a reference to compare how much is the redshift, which can be because of variety of reasons, but where do we get a reference to compare it with?
Yeah, okay. You can have redshift due to Doppler, you can have due to gravitation, etc. So this is where actually modeling helps. Many times in astronomy, what we do is we don't arrive at the final conclusion based on just the straight application of a particular principle. We apply one by one and veto certain considerations, and finally arrive at the final result. That is how, for example, we arrive at can this happen due to Doppler redshift? Can this be interpreted as that? Or can it be gravitational redshift, etc., etc.? And that is where we have to apply different models to see which one fits best. Yeah, does that answer your question, Devidas?
Yes, ma'am. But are there
And
different
especially,
possible
for
solutions?
example, if it is in a binary, there is a chance for Doppler shift. If it is not, then they may not be. All these. So it's not as if you can go straight and hit upon the final result immediately. You have to consider many things known about the source, and not only in the wavelength which you observe, it's also at the wavelengths with which others have observed of that source. And if it is a new source, like a new transient, then you have to collect the data to indeed find out what it is. That's where multi-wavelength observations are very useful to do this.
If you have any questions, you can raise your hands, students. There are no questions on the YouTube. Students, you can unmute and ask your questions.
So in the meantime,
So if you have no questions, you can also give me feedback, whether you understood my lecture, whether there was some problem, or whether it was too fundamental or too complicated.
it couldn't have been too fundamental. Nothing is too fundamental. I just wanted to ask, well, they're probably thinking, is there a kind of an email address or something in the ISRO website? Are there ways where people can contact for more information, or there is some kind of a website where they can go for the details after their interest is incited by your talk?
Yeah, there is, okay. At IUCA website, we have set up what is called the AstroSat Science Support Cell. Yeah, and that actually gives much of the details of the instrument. Primarily, it is for researchers who want to observe with AstroSat, but it also gives you what are the publications, which are some of the results, and so on. For the general public, we also created something called the AstroSat Picture of the Month in the Astronomical Society of India website. For the last few years, we have stopped it. We hope to restart it so that we can convey some of the results which are there from AstroSat. So that is one more the beautiful pictures obtained from UV imaging telescope. And you can also see the websites of the Indian Institute of Astrophysics for the UV images, and the other institutions. There are several academic institutions which contributed to AstroSat in the form of experiments, like TFR Mumbai contributed 3 of the experiments. Indian Institute of Astrophysics contributed 1 of them. IUCA contributed part of 2 of the instruments, and so on. So their sites also have some of the results which are coming out of this satellite.
Thank you.
Madam, may I ask one question? Our students, they are doing undergraduate BSc. So after BSc just completion, can they apply for some summer internship in this project, AstroSat? Are
Yes.
there opportunities?
Yes, many of the scientists at IUCAA, since I have retired from ISRO, I can't take anybody at ISRO, but many from IUCAA, TFR, ISRMO, many of the scientists working with this data can take summer interns. And they can also take MSc students who want to do projects from using AstroSat data.
Okay, thank you, ma'am.
So you will have to go to the respective institutes and see the options for the summer internship. ISRO per se is not offering summer internship for students, primarily because of entry restrictions, etc., for them to come and work. We are trying to work around that, but we so far have not achieved. However, if they can work with data at home, they can actually do it.
Yes.
There are workshops being conducted by the AstroSat Science Support Cell of IUCAA, where they actually tell you how to analyze data and so on.
There is a question by Satyam Pandey. Can you unmute and ask the question?
Ma'am, how can we determine radius and mass of a planet?
How can we determine mass and radius of a planet? Okay. See, every planet orbits around the sun, right? Take our solar system, for example. The planet orbits around the sun, right? It takes, for example, the Earth orbits, takes 365 days to complete the orbit around the sun. Now, if you know, so you can actually apply Kepler's laws to, you know, Kepler's third law, and you can find out based on the period and the distance of that planet from the sun to actually find out if you have an estimate of the mass of the sun, you can find out the mass of the planet by applying the Kepler's laws. And the radius of the planet itself is can be found by what we call as we can actually measure things which are very close in our solar system by what is called parallax. In fact, we can actually find the size of some of the nearby planets like Mars, etc., by resolving with large telescopes. And there you will see it as a disk rather than as a point object, which we see with the eye. So we can resolve them. But, and of course, with space telescope, definitely we can see them as disks. But before that, how do we observe? We actually see transits of these things. And so if you know one size, you can find out the size of the planet which goes through that transit.
There is a question by Abhishek Valmiki.
Yes.
Mr. Valmiki, you can unmute and ask the question.
Hello, am I audible?
Yes, please go ahead.
Yes.
Ma'am, what about the sun and exoplanets and neutron star? You said about planets, right? What about the sun?
Yeah.
If we don't know about the
What?
mass of sun and radius of the sun, then
Yeah. So, is the mass of stars essentially was initially determined based on stellar theories. Okay, based on there is something called the luminosity mass relationship, and so if you know how do you determine the luminosity? You can determine the flux And based on the flux, you can determine flux. When I say flux, sorry, the amount of radiation which you receive on the ground, you can actually determine the luminosity if you know the distance to the stars. And the distance is, there are many ways to find it. If it's nearby, you can find it by parallax method based on the Earth's orbit around the sun, etc. So if you know the distance, you can find the absolute magnitude. You can find, based on the luminosity mass relationship, you can find the mass of the star. Alternately, you can also apply the Kepler's laws. If you know the mass of the Earth, for example, or because you know the mass of several planets, you can again estimate the mass of the star also. But since the mass of stars runs into several thousands, say it is actually 10 to the power 33 grams or 10 to the power 30 kgs. So astronomically speaking, we don't mind whether it is 2 or 2.5 or so on for general purposes. But when you want to make accurate predictions, then the accurate mass of the sun is required. Does that answer your question? So, and you asked something about exoplanets. In fact, exoplanets, we can actually find the radius by the transit method. As it crosses the host star, the stellar brightness dims, and based on how long that dimming occurs, we will know the size of the planet, exoplanet. Yeah, we model it actually in terms of eclipses and so on. The eclipses are modeled. Yeah.
One question from YouTube. Does the stars really disappear or shed energy at some point of time and gain back later and come back again? By Bhanuvati Vishweshwaran. Ma'am, could you hear?
Okay. Do they, for example, become dark and then again brighten? Is that the question?
Yeah, some like stars really disappear or shed energy at some point of time and gain back later and come back again.
Okay, we haven't heard
Does
of
it happen? Yeah.
that kind of suddenly going off and coming on again, because these stars are huge balls of gases, and that kind of, for example, sudden disappearance and sudden re-emission usually cannot happen. Of course, if there are, for example, something happening in the atmosphere, for example, suppose at some day the Earth's atmosphere is clouded, say with a huge volcanic eruption, or due to some other phenomenon, you might stop seeing the sun, but the sun itself may not have stopped shining. The sun, of course, as I said, only due to evolution over billions of years might stop shining and it becomes a white dwarf, but it will still shine as a white dwarf. Yeah. So the luminosity may be lesser compared to the luminosity of the present sun, but it will still be seen as a faint object. Of course, the outer layers may expand at that time, and we humans may or may not remain on the Earth because it's expected to go beyond the Earth's orbital radius. But stellar system is so huge that I told you the radius of the sun is 100 times the radius of the Earth. So you can imagine these kind of systems, they can't just go on and off so quickly.
Madam, so we'll conclude the session.
There are, okay, having said that, I will add just one sentence.
Yes, yes.
Gamma ray bursts. Gamma ray bursts were thought to be things which come on and go off, that too in the highest energies, gamma rays. Now we know that they might be caused, some of them at least might be caused due to mergers of neutron stars or black hole, neutron stars specifically. And some of them might be what is called a hypernova or a bigger form of a supernova explosion. Yeah.
So let us just conclude. We thank IPA Secretary, Professor Dr. Vandana Nanan, for giving us the opportunity to host the event. We also thank all the IPA members, Dr. Aradhana Srivastava, Treasurer. We extend our sincere thanks to today's speaker, Dr. S. Sita, for such an enlightening talk on compact objects, studies using astrosat and showing us the results on planetary nebula, neutron star, black holes. And definitely students have so many questions. We'll write to you, madam, and they will be very happy to interact with you. Yeah. And we thank to BRNS for funding. We also thank Principal, Vice Principal, Management, BES, ASC, Vivekananda Education Society, College of Arts, Science and Commerce for extending support for today's lecture. And we thank all the students, teachers, scientists who are seeing the lecture in YouTube and also in the Zoom meeting. Thank you all. So we end the meet here. Thank you, madam.
Yeah, thank you so much.
Thank you, Dr. Sita. Thank you, Sarla, and thank you, everybody.
Thank you.